Hi everybody, and welcome to example 2 on page 56 of the workbook. And this is an example to maybe visually see what it is that we're doing when we calculate an improper integral. Okay, so in this problem, notice that they're giving us two functions, 1 over x squared and 1 over x. Those are these two pictures that we're looking at. And they're asking us to do two improper integrals. The integral from 1 to infinity of 1 over x squared, and the integral from 1 to infinity of 1 over x. Okay, so I'd like to do those one at a time, and then we'll kind of tie it together with a couple of comments here. So why don't we start with the first of those two integrals. Okay, the integral from 1 to infinity of 1 over x squared dx. Okay, well, we just talked about how when you have an integral like this where there's an infinity in the limit, the idea is to break the integral kind of into two parts and to first replace that infinity by just kind of a symbol. So we'll integrate from 1 to b, and then we'll take the limit as b goes to infinity. Okay, now before we do this integral, I'd like to demonstrate graphically what's really going on when you do that. Okay, so if you focus just on the integral part of this for a second, it's like saying we're going to integrate from 1 to some number that we're calling b. Remember what an integral represents graphically, it's an area. And so if you look just at the integral part, you'd be finding that area. But then there's a second piece to the calculation. We're letting b go to infinity, which is like taking this number b and picking it up and just moving it to the right off to infinity. And what that's going to do is stretch this interval that we're integrating over and pick up all of the area under the curve all the way off to infinity. So in a nutshell, what we're doing is finding all of the area under our curve from 1 to infinity using this two-step process. Okay, so let's clear away a little clutter here, and we'll see if we can actually calculate this now. Okay, so again, here's the area that we're looking for. And we need an antiderivative for 1 over x squared. Remember, 1 over x squared is really x to the negative 2. Okay, so if we do that, we are going to get, okay, let's see, antiderivative of x to the negative 2 is x to the negative 1 over negative 1, which we can rewrite as just negative 1 over x if we simplify a bit. Okay, so our limits are going from b to 1, so we need to take those limits and substitute them in for x. So the upper limit is b, that's going to give us negative 1 over b, and then we're going to get a minus negative, that's a plus 1 over 1. Okay, and now to finish, we need to calculate this limit. So the question here is, what happens as b goes to infinity? Well, notice where the b is. It's in our denominator. So we have a fraction that looks like negative 1 over something that's getting really, really big. What happens to a fraction again if its denominator goes off to infinity and the numerator stays constant? It's going to go to 0. So that negative 1 over b just goes to 0, and we get an answer of 1. Okay, so what we've discovered then is kind of an interesting fact. This area up here that we shaded is actually finite. Okay, even though the area goes all the way from 1 to infinity, there's a finite amount of that area. It doesn't get bigger than 1. Okay, so let's compare that calculation then with the other integral. They'd also like us to calculate the integral from 1 to infinity of 1 over x dx. Okay, similarly, that would be the area under the 1 over x curve from 1 all the way to infinity. And we'll do the calculation in the same way by taking the limit as b goes to infinity of the integral from 1 to b of 1 over x dx. Okay, so this time we need an antiderivative for the function 1 over x, which is the natural log of the absolute value of x. Okay, evaluated between b and 1. So substitute our limits in. And let's see, upper limit's going to be ln of the absolute value of b minus ln of the absolute value of 1. Okay, and one kind of nice thing happens here, the natural log of 1 is actually 0. So that second term goes away. And question then is, what happens if you take the limit as b goes to infinity of the natural log of b? Okay, the natural log function actually goes off to infinity when you plug bigger and bigger things in it, and so the upshot of it is we're going to get infinity out of this. Okay, so the area that we shaded over here is actually unbounded in the second case. Okay, so that area gets bigger and bigger and bigger and goes off to infinity according to our calculation. Okay, so just to kind of summarize, we got very different behaviors for these two integrals. We got a finite number for the integral of 1 over x squared, and we got infinity for the second one. So we would say then that the first integral converges to 1, whereas the second integral diverges. I'm going to write that down. Converges, and the integral from 1 to x of 1 over x dx diverges. Diverges again just means that we didn't get a finite number when we did it. We got infinity. Okay, one last comment maybe on the tail end of this example here. So you might have noticed that these integrals that we started with are pretty similar. They both look almost the same. 1 over x squared and 1 over x, the only difference really is the power on the x. We had a power of 2 in the first case and a power of 1 in the second one. So you might ask, could we predict when this integral is going to converge based on the exponent? Turns out we can, and so I'm going to close this discussion by filling in the little fact that we have down here. So anytime you have an improper integral of the function 1 over x to the p that goes from a to infinity, it turns out that it will converge if that exponent on the p is greater than 1, and it will diverge if p is less than or equal to 1. Okay, so we did an integral where p was 2, and we got convergence, and then an integral where p was 1, and we got divergence. That fits with what we have here. And this is a fact that we'll come back to a little bit later on in the course.